Before civilization, our early modern human ancestors faced a deadly ultimatum every single day: find safe water or perish. For 40,000 years, humans navigated the East African Rift, relying on hidden springs for survival.
Water emerged from rock cracks at a constant temperature, clear and free from visible surface pollutants. It was cold, odorless, and contained only essential minerals, a stark contrast to stagnant surface pools. Animals and humans carved deep, enduring paths to these springs, paths visible even from the air today. These trails ignored larger, more visible lakes, leading instead to specific, life-sustaining hidden springs.
No signs were posted, no tests were conducted, yet generations understood the difference through simple, repeated observation. For tens of thousands of years, every creature, including early humans, instinctively chose these springs over lakes. The human body is mostly water. Losing even 2% of your body weight in fluid triggers a cognitive decline. At 5% loss, severe fatigue and headaches set in, signaling the body's desperate need for hydration. 10% fluid loss causes kidney failure, and beyond 15%, death is inevitable within mere days.
3 days is the absolute outer limit for human survival without water, even under moderate climate conditions. Modern humans often forget this, but for our ancestors, 3 days was the operational window for survival. Every day, in every season and landscape, solving the water problem was essential to existence. Of all water on Earth, less than 1% is both fresh and accessible to humans.
The oceans hold 70% of our water, but salt water is undrinkable, forcing kidneys to work harder to excrete salt.
Most of our remaining freshwater is locked away in glaciers, completely inaccessible for daily consumption. What remains in rivers and shallow groundwater is a tiny, unevenly distributed fraction that is often invisible and dangerous. The danger was invisible, making the ancient water problem incredibly difficult to understand and solve. When we look closely at a single drop of water, we can see the individual H2O molecules that compose it. It took another 2 centuries after that discovery to link these tiny organisms to human disease.
Germ theory, the idea that specific microbes cause specific illnesses, was finally accepted in the late 19th century.
Scientists like Pasteur and Koch provided the definitive experimental evidence needed to change medical understanding forever. This was 150,000 years after our species first appeared, leaving the danger of water largely unexplained for most of history.
A crystal-clear river could carry Vibrio cholerae, the bacteria causing cholera, killing an adult in under 24 hours. Even a calm, pleasant pool could harbor Giardia, a microscopic parasite causing weeks of severe intestinal illness. Beautiful lakes often contain toxic cyanobacteria, blue-green algae, capable of causing liver failure. Yet, humans spread across every continent, populating every corner without filters, treatment, or knowledge of microbiology. A study modeled ancient human migration routes, mapping springs across 2 million square kilometers of East Africa. The researchers asked if early humans could have survived by walking between these water sources during the driest periods.
The answer was yes, but only barely, as these springs were spaced within 3 days of travel. We start with the scattered water sources across the region. Then, the invisible network quickly connects them all, ensuring efficient distribution.
The landscape itself is a water map. Plants cannot lie about water. Dense, green vegetation often signals subsurface moisture. Trees like willows and cottonwoods are phrydophytes, with root systems reaching deep to tap into the water table.
The tree has done the work that would take a human hours of digging to find water.
Animal behavior is the second signal. Large herbivores develop stable, repeated movement patterns to reach reliable water sources.
Birds are even more reliable trackers, as many species must drink daily and return to water before roosting.
Their flight patterns at dusk are purposeful and oriented, almost certainly heading toward water within a few kilometers.
Insects, particularly bees, are precise. A hive must be near water to regulate temperature, creating reliable flight lines. Morning fog concentrates in low-lying areas where moisture is higher, another indicator of subsurface water.
Depressions in hard rock, known as tinajas, collect rainwater and hold it far longer than soil, which allows it to percolate. None of these survival skills required formal instruction. They required attention and generations of passing down what was noticed.
Finding the water was half the problem. Deciding whether to drink it was the other half. Water that is bright green, the color of a cyanobacterial bloom, is almost universally dangerous. Ancient people observed that animals drinking from such sources got sick, which was enough to warn them away.
Sulfurous or rotting odors signal volcanic or organic contamination, another clear warning sign detected by the human nose. A river teeming with healthy fish suggests the water is not acutely toxic, though it isn't a guarantee of total safety.
Dead fish, or a lack of aquatic life where there should be some, is a serious warning sign. Water that emerges from underground has passed through layers of rock and soil, which naturally filters out surface contaminants. Ancient people recognized that spring water tended to be safer than river water. High elevation sources were safer than low ones, and water upstream was always preferable to water downstream. This principle, drawing water upstream but never downstream, became a formal rule in many ancient cultures. In communities where this was enforced as custom, waterborne illness rates were significantly lower.
Boiling is the most universal example. Heating water to 100 degrees Celsius kills virtually all harmful bacteria and parasites.
Ancient Sanskrit and Greek writings from 4,000 years ago explicitly describe these purification methods. Egyptian tomb paintings show people filtering water using wick siphons as early as 1500 BCE. In regions without fireproof vessels, some North American groups heated stones in fires to boil water in skin bags. Charcoal is another accidental discovery with beautiful science behind it. When wood burns incompletely, it becomes activated carbon, a material full of tiny channels and cavities. A single gram can have a surface area of 500 square meters, enough to trap organic toxins in water. Ancient Japanese households developed a charcoal tradition in water storage that persists today.
Sand filtration works by physically trapping particles and developing a biological film that consumes pathogens. Copper deserves its own discussion, as it is one of the most striking examples of empirical discovery in human history. When water is stored in copper, small amounts dissolve as ions, which are toxic to bacteria but harmless to humans. Laboratory studies have confirmed that copper vessels kill dangerous strains like E. coli and Salmonella within hours. The Romans built 11 aqueducts, delivering fresh water from springs and rivers into the city using only gravity.
Watch closely as we raise the right side. This is what we call a gradual incline, a very slight slope.
At its peak, the system supplied 300 million gallons daily to Rome's fountains, baths, and private households.
The city of Mohenjo-Daro, built around 2600 BCE, had a sophisticated drainage system that archaeologists found in the 1920s. Every time you turn on a tap, you are experiencing the compressed product of hundreds of thousands of years of human observation.
Organizations like water.org provide microloans to families in the developing world to build or connect to water infrastructure.
Water directs 100% of public donations to water projects, with GPS-tracked verification so donors can see their impact.
The science eventually caught up with the practice, but the scale of the need remains a critical challenge for our future.